This is talking about hypothesis testing and confidence intervals. The theory of hypothesis testing involves the fact that you take your research question and you develop it into a question for your statistical testing. We have type 1 and type 2 errors, which are called alpha and beta, and their influence on power. We have p-values, and we have looking at what's the difference between a z and a t-test, and distinguishing between a one-tailed and a two-tailed test, and looking at confidence intervals. So your research question is the first thing that you think about, and then you develop the null hypothesis, which is actually known as H0, and this is the hypothesis of no difference in your treatments, or no effect of your treatments on your particular response. And the alternate hypothesis, which can be denoted as H1 or HA for alternate, is that which opposes or is opposite to the null hypothesis. And since you've logically either got one or the other, you either do accept or reject the null hypothesis. And these are created in order to conduct statistical tests. In fact, we never really outwardly reject a hypothesis, we just fail to accept it, because we never know, there might be a situation where we do accept it. So it's about accepting and failing to accept. The type 1 errors are known as false positives. This error is known as alpha and is denoted by the Greek letter alpha. Type 2 errors are known as false negatives, and this is known as beta, the Greek letter beta. Power can be described as 1 minus beta, and this is the probability of rejecting the hypothesis when in reality it is false. The factors which influence type 2 errors therefore also influence power. Power increases when sample size increases, because this reduces the standard error, and when the sensitivity of the experimental test allows for small differences to be detected. We can summarise this in a table. We have got down here the reality. Is our null hypothesis true, or is our null hypothesis not true? So this is the reality, and then from our testing we make a decision. So we might fail to reject the null hypothesis, or we might reject the null hypothesis. So if we really do, or if the null hypothesis is true, then we should accept it or fail to reject it, and so that's the correct decision. If the null hypothesis is false, and we do in fact reject the null hypothesis, then we've made the correct decision. In the opposite cases here, if the null hypothesis should be taken as true, but we actually fail to reject it, that's a type 2 error. And likewise, if the null hypothesis is false, so that there are treatment differences, and we reject it, then we can make a type 1 error. P-value is the probability of getting the sample result, or a more extreme result, if the null hypothesis is true. When we refer to the significance level, or alpha, this is the probability of making a type 1 error, or a false positive. Unless a specific reason grants otherwise, it's typical for researchers to use alpha as 0.05, which gives a 5% chance of producing a false positive. When the p-value is less than alpha, the probability of getting the sample's result, if the null hypothesis is true, is less than 5%, which is unlikely, and in this case we reject the null hypothesis. When the p-value is more than alpha, the probability of getting the sample result, if the null hypothesis is true, is more than 5%, and in this case we fail to reject the null hypothesis. Here's something about z-tests and t-statistics. For both a simple z-test or a t-test, the test statistic is calculated using the following equation, where you have your mean minus your hypothesized mean, which is divided by the standard error of that mean, so it's s over the square root of n. The resulting critical value is checked against a tabulated value, or a value that you can get through R, such as a z value, which is derived from the Z distribution, and we use a t-table from the normalised t to get the t distribution. The limit to using the Z statistic in statistical tests is that it can only be used when the sample size is greater than 30, because otherwise the Z distribution is not quite normally distributed, and also if you have a known standard deviation or a sigma, then you can use a Z. That's really the case. Therefore, a t statistic would be required for a sample size of 30 and smaller, and is generally used. Here we're looking at one-tailed versus two-tailed, and you can look at this small diagram here. Figure A shows a two-tailed test. When you say that your alpha is 0.05, you're actually saying that you've got 2.5% in the lower tail and 2.5% in the upper tail. If you just did a one-tailed test, you'll be putting all of that 5% potentially in either the lower tail here or the upper tail. The term tail refers to the extremities on a graph, the tail of the normal distribution. Consider the research question involving two different wheat varieties. Does variety X use water more effectively or efficiently than variety Y? In order to determine this is a one-tailed or a two-tailed test, we must construct a null hypothesis and an alternate hypothesis. The null, if both varieties have the same performance on water use efficiency, and the alternate would be there is a difference in water efficiency between the two varieties. Since the alternate H1 is only interested in a difference without stating a direction, the test is two-tailed. Therefore, it investigates whether the critical value lies within 2.5% of either tail. When a t-test is two-tailed, the standard alpha 0.05 is divided by 2 and distributed to each tail. If, for example, H1 stated variety X is more water efficient than variety X, this includes a direction, and the test would be one-tailed. Lastly, confidence intervals. A confidence interval is a range in which the true mean lies around the sample mean at a given confidence level. We calculate an upper and a lower bound, and so this is our mean plus or minus, or this is our estimate plus or minus t multiplied by the standard error of that estimate. What does the 95% confidence interval mean? This means that the true mean for 95% of the time, or if you repeated it 95 times out of 100, the true mean lies within a calculated range around the sample mean. For a given two-sided hypothesis, if the value of the null hypothesis has a 95% confidence interval, the p-value is greater than 0.05. This relation shows that at a given alpha, the corresponding confidence interval is 1 minus alpha times 100.